Here is a straight line. Now watch what happens when I show you where it actually lives. That line we just called straight is curving around an entire sphere. So, this is the real question for the whole video. What does straight even mean when the space itself is curved? If you look up what a straight line means in different parts of math and physics, you can get three answers that sound completely different. In school geometry, it is the shortest distance between 2 points. In physics, it becomes the natural path through space-time. Here's the key thing to hold on to. These are not three different definitions. They are the same idea. What changes is the geometry of the space those paths live in. Once the space changes, the shape of a straight path changes with it. So before we do anything technical, we need one clean intuition for what straight really means. Imagine an ant walking on what it thinks is a perfectly flat surface. To the ant, every step forward feels like a straight line. No curves, no bends, just forward motion through flat space. But now, pull back. That flat plane was never flat at all, it was curved all along. The ant's straight path curves through space, bending with the surface. Same path, two completely different perspectives. This is the key insight. Straight does not mean globally straight, it means locally straight. The path of least resistance in whatever space you happen to occupy. The ant was right all along in its own way. But what if space itself is curved? In flat space, we intuitively know that the straightest path between 2 points is the shortest. Let's see this visually with 3 different paths from A to B. The wavy path wanders and wastes distance. The curved arc is better, but still not optimal. The straight line is clearly the shortest. In flat space, straight equals shortest distance. This is the mathematics behind it. The Pythagorean theorem tells us that the hypotenuse, the straight line across, is always shorter than going around the corners. But here's the crucial question. What if space itself is curved? In flat space, geometry behaves exactly as we learned in school. Draw any triangle on a plane, measure its 3 angles, and they always sum to exactly 180 degrees. But on a curved surface like a sphere, something strange happens. The straightest possible paths, called geodesics, are great circles. When we form a triangle from them, the angle sum exceeds 180 degrees. The excess reveals how curved the surface is. Here is the crucial insight. Flat space gives 180 degrees exactly. Curved space gives more. This angle excess is not a mistake, it is curvature revealing itself through geometry. So, what would our ant discover crawling on a surface it cannot see? What secret would its own triangular path reveal? Look at a sphere from far away and you see its curvature clearly. But zoom in closer, and something remarkable happens. The surface begins to look almost flat, like a plane stretching out before you. Zoom in enough and any surface looks flat. Now, watch this great circle path on the sphere. From far away, it clearly curves around the ball. But zoom in tight, and that same path looks perfectly straight, like a line on a flat table. Zoom out, and the curve returns. Straightness is always local. What seems bent from afar becomes straight up close. Here is the deep insight. Place a flat plane beside the sphere. Draw a short, straight arrow on the plane, and a matching short arc on the sphere. At this scale, they are locally identical. You cannot tell them apart. The difference only shows up when you pull back and see the full picture. Local geometry is universal. Global geometry reveals the truth. On a flat surface, when we transport a vector around a closed loop, something simple happens. The vector slides smoothly, keeping its direction fixed. When it returns to the starting point, it is exactly as it left, unchanged, unrotated. This is what we expect from parallel transport in flat space. But now, consider a curved surface. A sphere. We place a tangent vector at the north pole pointing south toward the equator. We move it south along a meridian. The vector stays parallel to itself locally, always tangent to the surface, never spinning. At the equator, we turn east. the vector continues pointing south in its local frame. But watch carefully from outside. In 3 dimensions, its direction is slowly rotating. Finally, we travel north back to the pole. The vector arrives home, but something is wrong. It has rotated 90 degrees from its original direction. Here is where it started. Here is where it ended. The rotation did not come from us turning the vector. It came from the geometry of the surface itself. Here we see 3 fundamental surfaces of geometry. On the left, a perfectly flat plane. In the center, a sphere curving outward. And on the right, a saddle surface curving in opposite directions. If straight depends on the space, what does straight look like in different worlds? On a flat plane, it's an ordinary line. On a sphere, it's a great circle, and on a saddle, it's the path that doesn't steer left or right. Despite the different shapes, they share the same idea. The path never turns within the surface itself. But how can a creature living inside the surface tell? Only by looking locally. Up close, both worlds look flat. The ant cannot tell the difference between a tiny patch of plane and a tiny patch of sphere just by looking at its immediate neighborhood. When the ant walks along a truly straight path, its own forward arrow does not twist or turn relative to the surface beneath its feet. Locally straight means no turning in your own frame, but on a wrong path, the ant feels itself bending left or right. Look closely at a tiny patch of any surface. On a flat plane or on a sphere, the local view is almost the same. Up close, straightness feels identical, but zoom out and extend the same locally straight paths. On the plane, they stay parallel. On the sphere, they slowly converge. Same local rule, different global result. Curvature does not announce itself in a tiny neighborhood. In flat space, geometry behaves exactly as we expect. Here we have a simple triangle with points A, B, and C on a flat plane. Now we place a vector at point A. When we move this vector along a straight path to point B, we keep it pointing in exactly the same direction. This is called parallel transport. Continuing around the triangle, from B to C, and finally back to A. Imagine a straight line on a curved surface, like the Earth. We call these geodesics. Let's draw a triangle using these perfectly straight paths, starting right at the equator. Now take a vector pointing north, and slide it along the equator without twisting it. This is parallel transport. The vector stays perfectly parallel to itself from its own local perspective. We continue along the meridian to the North Pole, and then back down to our starting point. Look closely. It's the exact same vector, but it's pointing in a completely different direction. This rotation is the fingerprint of curvature. The angle it turns is directly tied to the area inside the loop. So, how do we measure this? Here's the payoff. When we complete the loop on a flat surface, the vector returns unchanged. But on a sphere, something remarkable happens. The vector rotates. This rotation angle is the signature of curvature itself. The rotation isn't random. It scales with the area enclosed by the path. A larger triangle means more rotation. More curvature means more rotation. This proportionality is the key insight. This gives us a precise relationship. The total rotation equals the curvature multiplied by the area. Here are 3 fundamental geometries: the sphere with positive Gaussian curvature, the flat plane with zero curvature, and the saddle with negative curvature. Each color represents a different class of curvature. Watch what happens when we parallel transport a vector around a small loop on each surface. On the sphere, the vector rotates clockwise. On the plane, nothing changes. And on the saddle, the vector rotates counterclockwise, the opposite direction. A cylinder looks curved from the outside, but if you're an ant living on its surface, something surprising happens. When you parallel transport a vector around a loop, it returns unchanged. No rotation, no twist. The cylinder behaves like a flat plane. Here's why. The cylinder can be unrolled into a flat plane without stretching, tearing, or distorting any distances or angles. This means the ant cannot detect any curvature by measuring within the surface itself. Intrinsic curvature depends only on measurements you can make from inside. Now contrast this with a sphere. Try to flatten a sphere and you inevitably get distortion. Areas stretch, angles change. No matter how you map it, the surface resists becoming flat. The ant on a sphere can detect this curvature through parallel transport or triangle angle sums. The Gaussian curvature captures this intrinsic property. From Gaussian to Riemann. We've seen how Gaussian curvature beautifully describes curved surfaces in 2 dimensions, but our universe isn't confined to surfaces. We need a tool that works in any dimension for any curved space. Enter the Riemann curvature tensor. Think of it as a machine. It takes 4 inputs, 2 directions that define a small loop, a vector to transport, and an output direction. What comes out? The change in your vector after going around that loop. Here's what it measures. Take a vector, carry it parallel around a tiny loop, defined by directions A and B. When you return, the vector has shifted. Remember our journey around the sphere. We parallel transported a vector and found it rotated when we returned to the start. This rotation angle is exactly what the Riemann curvature tensor computes. The Riemann tensor takes 2 directions to define a plane, takes an input vector, and tracks what happens to it. It outputs the change in every possible output direction. This structure can be visualized as a matrix encoding all these transformations. Here is the key insight. Riemann tells us how space itself twists. In flat space, Riemann equals 0. Three ideas. Geodesics are the straightest paths a curved space allows. Parallel transport reveals curvature through rotation. Gaussian curvature is intrinsic. Straight is not absolute. It depends on the geometry you live in. Straight is not a property of the path. It is a property of the space. Every space has its own straight lines. So ask, what space am I in? And this is where Einstein enters. Geometry becomes the language of gravity. Why straight lines are a lie. Curvature, geodesics, and the Riemann tensor